So we begin chapter 5. The title is 8051 addressing modes. The definition which is given on the first as a first point is self-explanatory. So the various ways in which your CPU access the data, that is known as your addressing mode. And broadly speaking, there are 5 addressing modes, which are immediate, then direct, register, register indirect, and index. And among these 5, you people are already familiar with immediate, register, and direct. I mean, you guys are already familiar with these 3 type of addressing modes. You just don't know the name, but you have already used these 3 type of addressing modes. So if when I'll just give the example, you will understand, and it is actually very easy. Apart from these 3, there are 2 other addressing modes which are registered, indirect, and indexed, which might be a bit new to you, but then again, these are also very easy. I mean, this chapter is quite easy. Okay, these addressing modes and all these things are not that difficult. Another thing you should always keep in mind is look at the second point. These addressing modes are determined when the microcontroller or microprocessor is designed. That means once your device has been designed, it cannot be further changed by the programmer. I mean, the programmer cannot change the way these addressing modes work. So this was your, just the introductory portion of your addressing mode. Now let us try to complete all the 5 addressing modes today. Okay, let's see how much we can complete. But our target will be, we'll try to finish at least all the 5 addressing modes by today. Let us begin with the first one, which is immediate addressing mode. If any one of you face any problem while understanding, then don't wait to ask question. Okay, as I said, this will get carried on. So at the end, it will be like you will tell me that, sir, please repeat the whole thing from the beginning. Then that becomes a bit difficult for me. Okay, so whenever you face a problem, stop me right there and I will explain again. All these examples are also available in your book. If you want, you may write, or you may just concentrate to understand. It's totally up to you. To understand this immediate addressing mode, there are a few things that you should try to recall. Like the first field over here, these are known as mnemonics, and the second field are known as operands. This one is known as source operand, and this one is known, sorry, not source. This one is your destination operand, and this one is your source operand. Then we might have comments or labels. All these things we already discussed in chapter 2 most probably. So to identify immediate addressing mode, you will only look at the source operand. If your source operand is a constant, then we say that this is immediate addressing mode. And in immediate addressing mode, we always use this pound symbol or hash symbol, whatever you say. We always use this hash symbol or pound symbol, and the source operand will always be a constant. So first two example, there is nothing complicated. You have used instructions like this a lot of times before. Now look at this DPTR. Those who can remember very good, those who have forgotten, I'm just helping you recall. Your DPTR is a 16-bit register. Your program counter is also a 16-bit register, but your DPTR and program counter are two separate registers. Okay, don't get confused with these two. These are not the same register. Both of them are 16-bit register, but functionally they are different. And your DPTR can be divided into two 1-byte registers. If you divide it to, the first one can be individually accessed by DPH, and the lower one can be accessed by DPL. And the size of each one of these is 1 byte, and together they combinedly become 2 byte or 16 bit. So your DPTR is a 16-bit register. That means at a time you can move 2 byte sized number in this example. But if you want, instead of using this single instruction, you can use this instruction. I mean, these two instructions will give you the exact same result as this one. In the first one, you are moving the number 4521H directly to DPTR. In the next one, first of all, you are moving DPL, that is data pointer low byte, you are moving 21H in the low byte, and in the high byte, you are moving 45H. So together in DPTR, the number will be 4521H. So all these are examples of your immediate addressing mode. Is it understood up to this? Clear everyone up to this? Yes, sir. So moving on, look at on the right hand side. Count equate 30. So all of you already know what is the function of equate. We have discussed this. So tell me, after we execute this line, that is move R4, comma hashtag count, what will be the value in R4?
30.
Yeah, I mean, primarily you are correct. You got the main thing, but there is small catch.
Hex of 30.
Exactly, hex of 30. Okay. So 30 will be converted to hexadecimal format, and your hexadecimal equivalent of 30 is 1E. So your R4 will contain the value 1EH. Now this line where most of the students get confused, that move DPTR, comma hashtag my data. Try to understand what is this my data. I mean, there are 4 fields, right? Label, mnemonic, operand, comment. Among these 4 fields, what is my data over here?
Label.
Exactly. My data is a label. Remember, in your MuC, your label cannot contain any data. What I mean is, if you take a register, say R4, R4 has a specific address of itself, and R4 can contain data. Right? These are the two things your R4 can do. But if you look at my data, if you remember in our previous example, there was instruction like lcall delay was there, where delay started from origin 300, and the opcode for this instruction was 120300, right? If you remember from your previous examples. So what I'm trying to say, these 12 represents the opcode for this lcall, and this 0300 specifies the address where this label is located. That means your label always gives you the address where your processor is supposed to jump or where your processor is supposed to go. Unlike these registers, your label cannot contain any data. It cannot store any data. It can only store the address, it can only have the address. After saying all this, if I ask you now move dptr comma hashtag my data, what will be the value in dptr? After this line, what will be the value in dptr?
200.
Exactly, 200h. Now some of you might ask that, sir, if I write move dptr comma my data, then what will happen? I mean, if I remove this hashtag symbol or hash symbol, this type of instruction is illegal because it does not make any sense when you are using the label. So if you write move dptr comma my data, this is an illegal instruction. So you cannot use this instruction and it does not specify anything. But over here, you should always remember that whatever is the address of this label, like over here, you can see the address of this label is 200h. That will be stored in dptr when you write move dptr comma hashtag my data. Now, when I've written my data colon data byte America, when you are defining this, what is actually happening is in address 200h, you will have the ASCII of capital A. Then in 201h, you will have the ASCII of M. Then in 202h, you will have the ASCII of E, and so on. This is the significance. I mean, the ASCII of this, all the letters are stored from this address, and this address is preserved by the label my data, which you have transferred to data pointer by this particular instruction. Instead of this instruction, you could have simply written move dptr comma hashtag or hash 200h. This would have given you the exact same result of this line. There is no difference. Have you understood up to this?
Sir, where the letters A, M, E are being stored here?
Here I showed you in address 200h, it will store the ASCII of capital A. Then in 201h, the ASCII of small m will be stored, and so on. All these are RAM locations. No, sorry, is it RAM location 200h? 200h is not a RAM location. These are ROM location. I mean, for this particular example, all these three are being stored in the ROM. Is it understood?
Yes, sir.
Okay, any other question over here? If there are no questions, so let's move forward. All right, now, so these are the examples of register addressing mode. So what is the only difference? Instead of using the value, we are using the name of the registers, and also there is no hash symbol. So when you directly involve the registers, this is known as register addressing mode. Very simple. You have used instructions like this before. Okay, so in front of you, you can see 6 examples of 6 instructions. Can you tell me if there is anything wrong with any of these instructions?
Number five
three.
is not
Number
right.
three.
Number 3. Okay. First of all, I heard number 3. Okay. So
Fine.
tell me why number 3 you think is not right.
So the DPTR is a 16-bit register and the A is a 8-bit.
Exactly. So you cannot transfer data between 16-bit and 8-bit registers. Okay. So that's why this is a wrong instruction. Next, is there any other instruction which is wrong?
Number 2, sir.
Number 2. Okay. Why number 2?
Sir, the accumulator must be first, sir, as the source.
Okay. You got confused a little bit. Think you are correct. The accumulator must be first, but that is only during arithmetic operations like addition and all these things. But when you move, your accumulator can be then source as well. Okay.
Yes, sir.
Okay. But remember, you are right in one aspect. That is, when we go for arithmetic operations like addition, your accumulator must be the destination always. Okay. Any other register? Any other example over here which you think is wrong?
Five.
5. Why 5?
We cannot exchange data between registers.
Exactly. So register to register is not allowed. All right. So we have completed 2 type of addressing mode.
So,
One.
so accumulator is also one type of register, right?
Yes, accumulator is
So-
also one type of register.
So how can move R2, A is a valid instruction and not R7?
It's a special function register.
Actually, your registers like accumulator or B, these are known as SFR. They are registered, but they are known as SFR, like special function registers. We'll cover this thing a little bit later. But your question is valid at this stage because we know that A, B, all are registers. So this one we are saying is valid, but this one is invalid. The difference is because registers like this are SFR, that is special function registers. We'll cover this thing right now. I mean, after this point. Is it okay?
Yes, sir.
All right, so we have covered 2 addressing modes. First one was immediate addressing mode. The next is register addressing mode. Okay. Keep sure you remember the names and try to differentiate between all these things because very soon you will get confused.
Sir,
Follow.
sir, can we do move DPH DPL?
Can you do DPH DPL? Yes, you can do that. See, in the comment I have written over here, in the comment I have written Rn to Rn is not allowed, where n is equal to 1 to 7. Apart from this condition, you can move from any register to any register. Only Rn to Rn is not allowed, where n is equal to 1 to 7. Except this, everything else is permitted. Okay?
Yes, sir.
Okay, so the next addressing mode we have is direct addressing mode. And this one is also not new to you. You guys are already familiar with direct addressing mode. Let me give you some examples, then you understand. Again, it is not necessary to write. All these things are already there in your book. Okay, I've just tried to summarize a few things. The next one is direct addressing mode. You see the difference over here. In direct addressing mode, we use the address directly. We do not use any hash symbol. We do not use, we do not use any constant value. Rather, the address is directly involved. Look at the first instruction, move R0, 48. It means that whatever is there in the address location 48, please move those contents to R0. This is your first example. The second example, say it says that whatever you have in accumulator register, move the contents of all those accumulator register to the address 56H. So these are examples of addressing mode. If we keep going, look at these two. When you write move a comma 7, that means you are saying whatever I have in the memory location 7, please move that to the accumulator. And in the next one, this is actually not direct addressing mode. This is an example of what? Tell me. This one is an example.
Register addressing.
Exactly. This is an example of register addressing mode. So if you are in bank 0, if you recall from your previous classes, in bank 0, the address of R7 is 7. So in that case, these two will give you the same result. Understood up to this?
So can you repeat?
Again,
Which portion?
so the last one.
Okay, the last one. See, when we are in bank 0, if you recall, this is discussed in chapter 3 most probably. When we are in bank 0, the address of R7 is 7. So when you write move a comma 7 or move a comma R7, both of these will give you the exact same result. Could you remember? I mean, you have to recall the concept and address of bank 0, bank 1, bank 2, bank 3. Only then you can understand this one. Okay, so if you are having a difficult time to understand,
Sir.
let's try to say,
Sir, move A7, where what is the 7 is representing here?
what 7 is representing?
Yes, sir.
7 is the address location, any address location, not any address. I mean the address, the location whose address is 7, the memory location whose address is 7.
Okay, sir.
Sir, is it being addressed as a hexa number here, the 7?
It doesn't matter whether you consider 7 as hexa or decimal. Both of these will give you the same thing. The difference is only created when you exceed 9. After 9 in decimal we have got 10, but in hex we have got F. So up to 9, from 1 up to 9, all the numbers are same in both decimal and hex. So it doesn't matter. Okay.
Sir, what if 17 was written here?
What if 17 was written? That's a good question. So if you write 17 and if you do not specify anything like what type of number it is, then 17 will be considered as decimal, and your assembler will convert that 17 into equivalent hex, and that equivalent hex will be the location from where data will be fetched. Did you get your answer?
Yes, sir.
As I was saying, let us try to recall the RAM memory locations for those who have forgotten. From 00 up to 1F, this was separated for register banks where we had 4 banks. Then from 20 to 2FH, these were known as bit addressable memory. So let me just leave it like this. And then from 30 up to 7FH, these were known as your scratch pad RAM. And if you remember, in banks, we had 4 banks. They were bank 0, bank 1, bank 2, and bank 3. And all these 4 banks had 8 register from R7 up to R0. Same thing from, R7 up to R0. R7 up to R0, finally R7 up to R0. But all these different registers had different addresses. So when you are in bank 0, the address of R7 is actually 07. So when you write move a comma 7 or move a comma R7, they will give you the exact same result. Did you understand now? Have you understood? All right. Now you see, try to pay a little bit concentration over here. Your direct addressing mode is specifically used in this address 30 to 7F8. The question is why? You can use direct addressing mode in any location of the RAM. There is no problem with that. But it is preferred that when you are in the scratchpad RAM, you use direct addressing mode. So let me explain you why. See, when we are in the register banks, as I have shown you, we have got 4 banks. In all these 4 banks, all the registers has got some name. That means over here, you can easily use register addressing mode. Since the registers has a name, we can use register addressing mode. About this bit addressable memory, we'll learn this a little bit later at the end of chapter 5, because over here you can access the registers even as a single bit. So forget this for the time being. Okay, we'll learn this at the end of chapter 5. Now come to this scratchpad RAM. Look at this scratchpad RAM. In scratchpad RAM, these address locations do not have any name like R7, R6 or all these things. They only have their location or address. That's why when we are in this zone, that is when we are in the scratchpad RAM, we cannot use this register addressing mode. So we are only left with direct addressing mode. That's why when we are in this location, we use direct addressing mode. But when we are in the register banks, that is in these locations, it is up to you what to use. You can use either register addressing mode or direct addressing mode, totally up to you. But it is always suggested that when you are in the register banks, use register addressing mode, and when you are in the scratchpad RAM, use direct addressing mode. Is it clear up to this?
So can you repeat again
Which portion?
the last portion, that why can't we use register addressing mode here?
In scratchpad RAM, do you have any name of the memory locations? Like in this bank, I'm saying that in bank 0, the names of the registers are R7, R6, R5, and so on. Can you say the same thing for a scratchpad RAM?
No, sir.
No, but you see, in register addressing mode, we need the name of the registers. Otherwise, we cannot use register addressing mode. So since you do not have any name for the registers in scratchpad RAM, we cannot use register addressing mode. So in such case, we use direct addressing mode. Have you understood now?
Yes, sir.
Okay, anyone else? Any other question?
Sir, so until now, when we were using the register banks, we use, whenever we used R0, R1 or something, by default register bank 0. When use registers R0, R1 from other banks, we specified the PSW.
Exactly right.
When we are using the direct addressing mode using the addresses, we shouldn't be concerned with the PSW.
No. You don't need to worry about that because you're directly using the address. So you should not be worried about PSW.
Okay.
And look at this last example. Say, if you are in register bank, this one is equivalent to the instruction move R7, R2. But you know that this is invalid, right? Because Rn to Rn we cannot write. This one is invalid, but this one is a valid instruction. So if you consider, you might consider it as an advantage also. But anyway, move 7, 2 is a valid instruction, but move R7, R2 is an invalid instruction. Can I move on?
So move 7, 2 is a valid.
Yeah, move 7, 2 is a valid instruction.
Okay, sir.
Now let us discuss about SFR registers that we just heard a little while ago. So these are known as your special function registers. Some of the SFRs are A, B, DPTR, PSW, SP. There are a lot of other SFR registers as well. The important thing to notice is that these registers can be accessed by their names or by their addresses. I mean, totally up to you. So far, you only know that the address of register A is 0E0H. Now you see the address of register B is 0F0H. So if you write move 0F0H, 25H, or if you write move B, 25H, both of them signify the same thing. There is no difference between these instructions. Okay. If you want to see the other SFR registers, you can have a look at table 5.1 of your book. In your table 5.1, all the SFR registers along with their addresses are given. The main thing, you don't have to memorize the address of any of this. I mean, it is better, at least if you can remember the address of register A and B, but it is not necessary to memorize. Just look at the table and try to understand what they are saying. I mean, the registers, they all have got different addresses. So just try to see those things. In the exam, if you need this table, then you will either be provided this table or the required data will be provided to you. So bottom line is you don't have to memorize this table, but at least you should know that there are some SFR registers and they have some corresponding addresses. Clear up to this? Is it okay up to this? Can I move on?
Yes, sir.
So again, try to recall whatever we have learned in this class. So we started with immediate addressing mode, where we transfer the values directly using the pound symbol. After that, we have learned about register addressing mode, where we use registers for moving or transferring any data or for the mnemonics. Then we have learned about direct addressing mode, where we use the address directly. And as I told you, all these three are already known to you. So let's try to complicate things a little bit, okay? That is, in everything we'll try to incorporate stack. Okay, I think it is better if I give you an example rather than writing the definition. If I tell you something like this, say, I have got bank 0 over here. I have got the registers R7, R6, R5, 4, 3, 2, 1, 0. Okay, in bank 0, can you tell me what is the address of register R0?
0.
Exactly. So it is 0, 1, 2, 3, 4, 5, 6, 7. Now I'm asking you, write a code that will store the values of R6 and R5 onto the stack. What will you write? Write a code that will store the values of R6 and R5 onto the stack. So what will you write?
Push 6, push 5.
Push 6 and then you wrote push 5. Now if I tell you that pop out the values that you have pushed into R2 and R1, what will you write?
Push 2 and push 1. I pop 2 and pop 1.
Exactly, pop 2 and pop 1. What I'm trying to say is, during push pop operations or during stack operations, you can use only the direct addressing mode, because in all these cases you are using the address. Say you are not using the names, you are using the address only. Since for all the push and pop operations you can only use these addresses, your push pop or stack operation is only accessible by the direct addressing mode. Understood up to this one? Is it clear? Is it okay to all of you?
Yes, sir.
Now let us try to see an example. Again, this example is from the book. If you do not want to write, totally up to
In
you.
the previous slide, if I wrote POP 8, will it go to the bank 1
It will,
R0?
if you write POP 8, it will go to registered 0 of bank 1.
Okay, sir.
Okay, as I was saying, this is the same example of your book, example 5.2. If you don't want to write, that is fine by me. I have no problem with that. First of all, to understand this solution, you have to look at the problem statement. So try to understand the problem statement. The problem statement, I'm writing it short. It says that you have got some data in registers A, R0 and R1 of bank 0. You need to transfer this data. You need to transfer this data to register B, R0 and R1 of bank 1, and there is small condition given, that is you have to use stack operation. So let me say what is the problem statement. So the problem statement says transfer the data that is stored in register A, R0 and R1 of bank 0 to register B, R0 and R1 of bank 1 using the stack. So let me give you the solution. After that, let me explain, then you can ask any question. Okay. Let us try to understand the solution. The first line, we are moving the stack pointer. We are moving 3fh to stack pointer. Can anyone tell me why we are doing this? Can you tell me why we are doing this?
What was the question, sir?
For moving to the Scratchpad RAM.
The question was, I have got some data in register A, R0 and R1. I need to transfer this data of bank 0 to register B, R0 and R1 of bank 1. My condition is I have to use the stack to perform this operation. So the first question was why we moved 3fh to stack. The answer someone gave me was to use Scratchpad RAM as stack. So the question still stands. Why do we need to use the Scratchpad RAM as stack other than our regular stack?
The bank
we are
1 is
using
already the stack. So if we move to bank 1, it will modify the stack.
It might create overlapping. Exactly. So that's why I've created default column. See, by default, the value of your stack pointer is 07. That means by default, your bank 1 is the stack. But look at the problem statement. The problem statement already involves bank 1. So our target should be not to involve bank 1 in any other type of operation. So that's why we do not use want to use the regular stack, which is bank 1. Rather, if we need extra stack, we can use the scratch pad RAM. That's why we have written stack pointer, comma, move stack pointer, comma 3f8, so that your stack is shifted. Clear first line, everyone? Is it understood? Is the first line understood to everyone?
Yes, sir.
No, sir.
Okay.
So
Which portion you did not understand? Tell me.
So if I use the initial value 07, what kind of problem do I have?
All right. So, see, I have written bank 1 over here, right? Initially, the value of the stack pointer is 07. So, if you write a push instruction, when you are writing push 00, that means whatever is there in this address will be pushed to the stack. So, tell me, if the value of the stack pointer is 07, where will it be stored?
08, sir.
Exactly, it will be stored in 08. Then when you write push 01, it will be stored in 09. When you write push 08, it will be stored in address A. So you are already using these registers for performing the stack operation, but your problem statement says that finally the values should be in these registers. But you see, when you are using the stack register, these registers are already being occupied. So it might create some overlap. Did you get the answer?
Yes, sir.
So that's why we are shifting the stack so that our default stack is not touched. I mean, bank 1 is left as it is. We do not want to disturb bank 1. Understood up to this?
Yes, sir.
So
If
could we have used bank 3?
No.
I mean, instead of
No. If you need extra stack, you can only use the scratch pad RAM. You cannot use any other banks as stack.
okay, sir.
If I go to the next line, push 00, tell me where will the value be stored? In which address the value will be stored?
40.
Exactly. So the address will be stored in 48, and the address will in this location the content will be the content of 00, that is content of R0. So 40 will contain the content of R0. In this next one, what will happen?
41.
41 will contain the content of what?
R1.
Exactly, R1. Then in this instruction, what will happen?
42.
42H will contain the content of
A.
exactly, right. Now what is happening in this line?
We are switching to bank 1.
Do we need this line? If we can just
These are two different things. The first thing is the answer is correct. Using this instruction, we are switching to bank 1. That is correct. Next is, do we need this line? For this particular example, you actually do not need this line, but this one is intentionally showed over here so that you know that at the in the middle of a code, when you are writing a code, in the middle, if you need to switch to different register banks, how can you do that? In order to demonstrate that this instruction is given. But in direct addressing mode, you need not bother about the PSW register. Okay? Is it understood?
yes, sir.
Now, when we go for pop 0F0H, what will happen? The value of 42H will go to register B, right? Isn't it?
Yes, sir. Yes, sir.
So B will contain the value of A. I'm just writing it in short because I need to write another thing. After this line, what will be the value of stack pointer?
41.
Exactly, 41H. In this line, it is very simple. When you write 9, your R1 will contain the value of 41H. That means of R1. So after this line, what will be the value of stack pointer?
40X.
48. In the last line, 08 is where is the address? 08 is this address. So R0 will contain the value of 48, which is of R0, and the value of the stack pointer will be
3FH.
okay. See, this is known as balancing the stack pointer. you have got stack pointer 3fh, you started with 3fh. So you should keep in mind that your stack pointer should always have the same value from which you have started. That means your code should contain equal push and pop instructions. Otherwise, next time when you go to use the stack, you might get a wrong result. Is it understood this example, everyone?
Yes, sir. I have a question. When do we actually need to change the bank? We already, I mean, we know the addresses 0908, so we can use those addresses to specify the bank registers. Then
So I got your. You will get your complete answer when we go to chapter 6. Still, for the time being, let me give you a small idea. See, by whatever you have learned so far, using this knowledge, you can add at best 2 1-byte numbers, right? And the result can be maximum 2 bytes, isn't it? Are you getting my point?
yes, sir.
If I tell you, if I give you a 32-bit number and I tell you add the 32-bit numbers, I mean, can you figure out how you will accommodate the result?
In 2 registers.
Your 2 register gives you 8 plus 8, 16. The numbers itself are 32 bits.
Okay.
So it gets complicated, right?
Yes, sir.
So what happens is, just after this, you will see that I have got another thing which is known as your register indirect addressing mode. Over there, you will see that you need pointers to point to addresses. Okay. So these registers, I mean, within a code, these registers become insufficient to store the address. So you need to constantly switch between different register banks to accommodate your result. Is it okay?
Yes, sir.
I mean, it might sound a bit hazy because until and unless I give you the complete example, you will not understand. But you need a little bit preliminary knowledge to understand that portion. That you will learn before mid, inshallah. Don't worry, before mid you will learn that.
Okay, sir.
Okay, any other question, anyone?
Sir, you said that we will be lacking registers to store data. We use the equate function and do the task because it will not assign any storage and we will also get the memory addresses.
Okay, listen, when I'll go to chapter 6, okay, when I'll show you that example, after that, you try to point this, I mean, just try to note it down. And over there, you try to give me an alternate result. Then I will accept that, okay?
Okay.
Sir, what do you mean by register A of bank 0 and bank 1 B register?
No, see, when I've written bank 0, I have underlined except A. When I've written bank 1, I have underlined except B because they do not belong to any register bank. Your R0 and R1 belong to register bank, and these R0 and R1 belong to register bank. Okay, A and B does not belong to any register bank. They are SFRs.
Yes, sir.
Any other question, anyone?
Sir, if it was a different bank rather than bank 1, so in that case, should we needed to set the set bit as
No, you could have used your usual stack in that case. No problem with that.
Okay, sir.
Now let us move on to the next type, which is register indirect addressing mode. Now this one is a bit new to you. The next addressing mode is register indirect addressing mode. Okay, so try to understand since it is new to you. So in this mode, a register R0 or R1 is used as a pointer. So the first question is, can anyone tell me what is pointer?
Sorry, we learned it in C programming.
Exactly, you learned it in C programming. So try to recall, what is a pointer?
Point to the address.
Right. A pointer is something that always points to the address. So you see that it is written in this mode a register, and that register can be either R0 or R1. You cannot use any other register except R0 and R1 as a pointer. So you can use only these two registers as a pointer to point to the data which is stored inside the CPU. Like look at the first one, which is written as move a comma at the rate R0. So it means that whatever value is there in R0, take that as an address, go to that particular address, whatever content is there in that address, transfer those contents to accumulator A. Again, I am saying it means that transfer the contents of RAM location whose address is stored by R0 into accumulator. Did you understand? It will be much clearer when we will see an example. For the time being, just know that at the rate R0 will point to an address. So from that address, you will fetch the data and you will transfer that to accumulator A. If you go to the next one, it is just the opposite. I mean, whatever you have in register B, that will be transferred or moved to the address which is stored by the register R1. It will be much more clearer when we'll go for one example. Forget about this point, forget about this point. These 2 points also you will understand when we'll see the example. But for the time being, look at R0 and R1. Both of these are 8-bit registers. So since they are 8-bit registers, they cannot point to a data which is outside the CPU, that is outside the RAM. If you remember, you have only 128 bytes of RAM. So within the RAM location, your R0 and R1 can point to any address. But when we go for ROM, if you remember, your ROM has 64 kilobyte of address. And also we can have externally connected RAM. So in order to access this ROM or externally connected RAM, we need a 16-bit pointer. So in such a case, we cannot use R0 and R1. Only in those particular cases, we can use DPTR register as a pointer. Have you understood up to this, whatever I've said?
The last part, sir. Sir, the RAM.
Okay,
This
RAM.
point, sir.
Okay, this point. See, when in the ROM you have got 64 kilobyte of memory location, in order to store those memory location, you need a 16-bit pointer or 16-bit register, because all these addresses are in 16-bit. 64 kilobyte, try to remember, to represent 64 kilobyte memory, you need 16-bit number, right? Isn't it?
Yes, sir.
So the address in the ROM area will definitely be in 16-bit size. So in order to store that address in a pointer, you definitely need a 16-bit pointer. But your R0 and R1 are 8-bit pointers. So we cannot use R0 and R1 to point to an address which is located in ROM or external RAM. In those cases, we need 16-bit pointer, and as such, we use the data pointer register. Have you understood this now?
Yes, sir.
Sir, only DPTR can be used, no PC.
Exactly. No, nothing else. Only DPTR can be used. You cannot use any other register as a pointer.
Sir, inside the CPU means the RAM.
Inside the CPU means RAM, right? Clear up to this? Now let us take an example. Then for those who are still confused about these two, and I still did not explain these 2 points, so it will be very clear. Again, writing is optional. This is there in example 5.3, the exact same thing of your book. So the question is copy the value 55H into RAM. I'm writing it short, okay? RAM memory locations 40H to 45H. Okay. So there are three solutions. Let me write the solution after that I'll explain. All right, so the question was copy the value 55H into RAM memory locations 40H to 45H. In the first condition, they said that solve this using direct addressing mode. So this one is definitely your direct addressing mode. So what we are doing, we are moving 55H to A, and then the address is given. So we just write move 40H, A, 41H, A, then 42H, 43H, and so on. So this one is very simple. In the next column, they said that use register indirect addressing mode without loop. That means you cannot use a loop. So what we did, move A, 55H. So A contains 55H. Then move R0, hash symbol 48. Okay, that means after this line your R0 will contain the value 48. Then you are writing move @R0, A. That means whatever is stored in R0, consider that as an address. So 40H will be considered as address, and move A to 40H. That means this line is exactly same as this line. Instead of writing move 40H, A, you are writing move @R0, A. Then you are incrementing R0. That means now R0 contains the value 41H. So this line is exactly same as this line. Move @R0, A. That means move 41H, A. Move the contents of A to 41H. Then again you increment R0. So now R0 becomes 42H, and the same process continues. Clear everyone? Up to this, the first two, is it understood? Is the first two understood to all of you?
Yes, sir.
So the last one is very simple. We just have to use the loop. So first line is simple. Move A 55H, move R0 40H. I mean this location, the starting location. Then we are writing a counter. This will act as a counter, and we are storing 05 because we have got 5 memory locations. Okay, so we are storing 05 over here. This exact same thing which is there, I mean this code, whatever is shown over here, this has been represented in a single loop. So what you are writing, move @R0, A. So for the first time, the value of your R0 is 48. So when you write this instruction, this is similar as move 48, comma A. Then you are incrementing R0. So R0 is becoming 41H. You are decreasing R2. So initially R2 was 5. Now R2 becomes 4. It is still not 0. So you go back to this level. You execute this line. So now this becomes equal to move 41H, comma A. Again, you increment R0. So R0 becomes 42H and decrease R2. R2 becomes 3. Again, you jump over here. And now you perform move 42H, comma A, and so on until and unless your R2 becomes 0. This is also, I mean, very straightforward. So did you understand all these 3 examples? If you have any question, you can ask now. Okay, so I left 2 points over here. This one I hope you understood. The third point says in this mode, accessing data is dynamic. See on the second column, you are using the same R0, but every time you are accessing a different data. But on the first one, to access different data, you needed different memory locations or different instructions. So that's why it says that accessing the data is dynamic. It is not static. And looping is definitely not possible in this direct addressing mode. You cannot loop over here. Looping is only possible when you go for register indirect addressing mode. So we have finished 4 addressing modes. We still have another addressing mode left and we have only 2 minutes. It will take at least 15 minutes completed. Okay, I think we will finish it in the next class. Have you understood up to this, whatever we have discussed in today's class? Yes, no?
Yes, sir.
Yes?
Yes, sir. For the loop. For the loop, I have a question. DGNZ, the jump occurs first, or the decreasing of the R2 register occurs first?
Decreasing occurs first.
So at first it will decrease to 5 to 4, then jump. Then again it will decrease to 3, then jump. Then 2 to jump, then 1 to jump, and after that it will decrease to 0. In that case, will it jump or will it?
No, it will not jump. See, the full form is decrease and jump if not 0. So that means decrease, then check the condition, then jump. Decrease and jump if not 0. Is it okay? So decrease first, check the condition second, jump third. Is it okay?
Then sir, the loop will run for 4 times.
Exactly, it will run for 4 times. Look at the first example. The last line is move 44H, comma A. When it says 40H to 45H, it means from 40 up to 44. 45 is not included. Clear?
Yes, sir.
Good question. These are actually small things that you should be careful about. These are not something for which you lose your entire mark, but these are enough to prevent you from getting the full mark. So you should be careful about these small things as well. So good question.
Direct addressing mode seems to be faster, I think.
Direct addressing mode seems to be faster. Yeah, you're right in that case. Direct addressing mode can be faster, but direct addressing mode has got a lot of limitations. So that's why we need indirect addressing mode. The advantage, as I said, the advantage of this indirect addressing mode, and after that you will see index addressing mode. This will be much more clear when we go to chapter 6. Over here, we are simply introducing you with the addressing modes, but the application you will see. By the way, did you do your own section? You are section B, right?
Yes, sir.
That means you still did not perform the lab. So in the next lab, you will see the use of all these things. Over there, you cannot use direct addressing mode. You will understand it tomorrow. Those who have the lab tomorrow, you will understand it. Okay?
Yes, sir.
Okay, so let me stop sharing. I'll just take your attendance and after that I'll let you leave.